Hello, everybody. Welcome back to AP Physics 2 review. We're going to be looking at Unit 3 free response type questions. We're going to be looking at 2 today. So, in our first question, we happen to have a sphere, and it reads, students are investigating the electrical charging of objects that have conducting sphere 1 that is suspended from an insulating ring as shown in the figure. They rub the sphere with a cloth to charge it, and they want to determine the sign of the charge on the sphere. They also have the following equipment. They have conducting spheres of various sizes that can be hung on strings, and they have a pair of parallel conducting plates, each plate of which can be given a positive or negative charge. And so for part A, they want you to describe a procedure the students could use to determine the sign of the charge on sphere 1, including the measurements to be taken or observations to be made. My microphone here in position. And so for this sphere response, for those of you here in the chat, let me know if you'd like some time to think about it or if you want me to just jump into the explanations or the approach here for these. Okay, let's see here. Okay, not sure about this one. Works either way. Okay. Alrighty, so let's go ahead and see here. So the idea here is that if we rub the sphere with a cloth, we're going to be able to deposit, or not deposit, but make a charge on it. We don't know if we're depositing electrons or removing them based on the cloth and the metal here, or the sphere. But they tell us a couple of things. For instance, they tell us that it's a conducting sphere. And so we should be thinking, well, this is a metal with generally free electrons. Maybe, just maybe, we're able to strip some away, but that doesn't matter here. And they want us to determine the sign of the charge on the sphere. And we have the following equipment. So I think the idea here is that if we have something that is known to be positive or negative, after we rub the sphere and it develops some charge, we can see whether or not it's attracted or repelled by one of these. So I would say something along the lines of um, the hanging sphere can be rubbed. Marking it. Okay. Then we could place, or then they can place one of the charged plates in the vicinity of the sphere. The idea being that and so I guess we'll just choose one of these because it could be a little vague here. Right now it reads, well, if we place one of those plates, how do we know, if it's positive or negative? So if the sphere is repelled by the positive plate, or attracted to the negative, the sphere has gained a positive charge. Any questions? That's- Okay. And so the idea is there's going to be some amount of deflection either towards or away from the sphere. And so, and we could take the other, I don't think we need to be super redundant here, but we could also say that if it's repelled by the negative plate and attracted to the positive plate, then the charge would be, the sphere would be negatively charged. If the opposite occurs, I think we're good here. Let's go ahead and look at what the College Board was thinking in terms of how they would have worded it. So let me go ahead and make a little more space here just to be able to fit it here. Let me pull up the one or AP Classroom and let's go ahead and see their scoring guideline. This is kind of what they were looking for. Give the conducting plates charges of opposite signs, noting which is positively charged and which is negatively charged. Place the sphere between the plates and observe its deflection. Oh, okay. So we could even do both at the same time. Okay. And so if it's deflected away from positive, it is positively charged and vice versa. You know, I was going to say vice versa here, but yeah, whatever. Okay. So the hanging sphere can be rubbed, charging it. Then they can place one of the charged plates in the vicinity of the sphere. And so here, I don't know if I'm being explicit enough that we would note which one is positive and negative, where here they say noting which plate is positively and which is negatively charged. So I think maybe I get 2 out of 3 on this one. Similar process. Just moving my microphone here. Okay, let's go on to the next question. The students now want to determine whether the same amount of charge is deposited on sphere 1 each time it is rubbed with a cloth. They carefully rub sphere 1 with a cloth using the same motion each time. They then touch the sphere, and let me bring out my highlighter just in case. Same amount of charge is deposited each time it is rubbed. They then touch sphere 1 to an identical sphere 2 that is fixed in place and release sphere 1. They adjust the position of the top of the string so sphere 1 is aligned horizontally with sphere 2 as shown in the figure. So basically they don't want us to get too fancy with the angles and the directions. We're just going to try to align them horizontally so that the force between them is horizontal, as shown in the next figure. The students measure the angle that the string makes with the vertical, theta. So that's going to be from here. And they label it. So I'm being a little redundant here. They discharge the spheres and repeat the process, each time counting the number of times they rub sphere 1 and making sure the distance d between the spheres is the same. Okay, so that's nice. They're holding something constant here. So they're going to do some kind of deflection. And I'm going to assume d, the distance between the spheres, is the same. I think it's going to be, oh, no. Okay, because it'll just, as sphere 1 deflects, they'll keep that fixed distance between them, but they'll move sphere 2 with it in this instance. Okay. So the idea here is when they charge sphere 1, it develops a certain amount of charge, and they say, assume that each time sphere 1 is rubbed with a cloth, the same amount of Q of charge is deposited after N rubs with the cloth, giving the net charge of sphere 1, or the net charge on sphere 1 is N times Q, the number of times rubbed times Q. And they ask, what is the net charge on spheres 1 and 2 after they have been touched together? And they want us to indicate what property of the spheres is responsible for this distribution of charges. Okay, so let's go ahead and see here. So because the spheres are identical, and that's this part right here, they touch sphere 1 to sphere 2, and sphere 2 happens to be identical. So we charged one guy, and then we bring sphere 2 in contact with it, and it's exactly the same, and they want us to find out what is the net charge. Well, Originally, sphere 1 has a charge of n times q, and sphere 2 has a charge of 0q. There's no charge on 2, but then they touch. And you don't need to draw this diagram. I'm just doing this here for you guys to like, I guess, kind of visualize the scenario. And then once they touch, because they are identical, they are going to get equal amounts of charge between them. So sphere 2 and sphere 1 are going to have n times q over 2 charge. So the spheres, and let me know if we have any questions so far. The spheres each have a net charge of n times q over 2. Now, if one sphere was bigger than the other, and this is more of a physics C question, but if one sphere was bigger than the other, then the bigger sphere would end up taking more charge. And that's because we could distribute it more on the surface. Because what ends up happening is charge is going to flow based off of electric potential. And electric potential we saw is kq over r in magnitude. So as the radius gets bigger, there is less and less potential on this surface. So more charge is going to want to flow until the two potentials are equal. So let's say the potential of sphere 1 equals the potential of sphere 2. Charge stops flowing when this happens. Remember that we say that charge flows from high potential to low potential. So if the two potentials are equal, then we can say kq1 over r1 equals kq2 over r2. And the k's don't really matter. And for the bigger sphere, bigger radius, we're going to need more charge to equate the potential of a smaller sphere with less charge. And I say it's a physics 2 concept, but I wouldn't be surprised if they asked you that as like part 3 of a question. You never know. So we're going to say that the two spheres have a net charge of n times q over 2. And the reason this happens is the spheres because the spheres are identical and conducting. Really important. Charge would not flow if one of these guys was insulating. And so if they touched, it really wouldn't do anything because charge would not be able to be deposited on one. The charge always distributes itself on the surface. And for this to occur, they need to be conducting. Sorry, charge always distributes itself on the surface for conducting materials. And conducting. So there's part B. Let me know if we have any questions so far. In the meantime, here's some nice calculations in algebra. Oh, and in case we wanted to see what the College Board was thinking, let me go ahead and pull up their scoring guide for this question. And so let's create a little more space here. And so the spheres will each have a net charge of nq over 2. The property of the spheres responsible for the distribution of charges is that they are conducting. Okay. So pretty much. Let's go on to the next one. Show that the angle theta can be related to the original charge q on sphere 1 by the equation tangent of theta equals some junk here. So basically they're telling us what it's equal to. And the reason they're telling us this is because if we need to use this equation later on, we can make some conclusions off of the equation without worrying about our bad math. But here they want us to try to prove this equation here. So let's go ahead and see what's going on. So sphere 1 is going to experience a couple of forces. Oops, I put that one. Sphere 1 has a gravitational force, Fg. It has a tensile force, and it has an electrical force due to sphere 2. Now, if we look at this tangent of theta, chances are we're going to want to work with sphere 1. Simply because sphere 2 is just sitting there on the floor, and friction is probably the thing that's keeping it from moving. Sphere 1. Okay. So here's our free body diagram, but as we've learned, if the forces are not perfectly aligned with our coordinate systems, we need to break it up into components. So I'm going to go ahead and say up is positive, and to the right is positive as well. And this will be for like positive x and positive y, or positive horizontal, positive vertical. All right, so let's go back to it. So we have the electrical force, which we can calculate using Coulomb's law, and we'll eventually substitute that in. We have a vertical component of our tension, Ty, and a horizontal component of Tx. Now here I'm going to have to try to make sure that these arrows are equivalent in length, because this sphere 1 that is hanging from the string is going to be in equilibrium. It's going to balance out. At the same time, this guy has its gravitational force, about that big, force due to gravity. Okay. So let's go ahead and do a little geometry real quick, just so that we know how big is Ty, Tx in relation to the angle. So because the angle is measured from vertical, hopefully we remember there's the gotcha here. Tx is going to be T sine of theta, and Ty is going to be T cosine of theta. Let me know if we have any questions in the chat so far. Okay. And I'll keep looking at the chat, but I'll continue right here. So if we look at Newton's second laws in the x direction, and I think you guys even had a question on Quest like this one. So I hope that this doesn't seem too foreign to y'all. But if it is, good thing we're going over it. So in the x direction, we have the electrical force minus the tensile force in the horizontal direction is going to be m times ax. And I'm just being real general here. We're just kind of going through all the steps here. We don't need to do all this because they're not even like having us derive the equation. They don't say derive, they just say show. So we could just kind of like skip a couple of steps and we're good. So we have Ty minus the force due to gravity equals m times a in the y. And the beautiful thing is, because this whole object is in equilibrium, the accelerations are 0. And we can go ahead and say that the electric force, which we'll make all these substitutions here eventually. And that looks like iron, so I'm going to write that as like, yeah, I went from capital to lowercase. Equals the horizontal component of our tension, and the vertical component of our tension equals the weight. Okay, so let's go ahead and see here. T cosine of theta, almost made a mistake, equals the force due to gravity, which is m times g. Alrighty, our equation has mg in it, so we're approaching something that looks decent. And then the electrical force is going to be given by K. I'm just going to do the general part here for now. Q1, Q2, all over R squared. And that's going to be T sine of theta. We should ask ourselves, well, what is Q1, what is Q2, and what is R? Because if we notice, they want us to use their variables. So when these guys are charged, we said that the charge of sphere 2, Q2, is going to be N times Q all over 2. It got half the charge. Let me just kind of break this up in space. At the same time, we said that Q1, the charge of sphere 1 here, is also N times Q over 2. So we're going to need to substitute this in here. And I'm going to make a little more space. So combining these ideas for Q1 and Q2 into this monster equation, we start to get Coulomb's constant K times, and let me put it in parentheses, NQ over 2 times NQ over 2. And we should start thinking, okay, well, are we approaching something that looks like their equation? Well, shoot, we've got K, we have N times N, that's N squared, and then we got Q and Q, that's Q squared. 2 squared is 4. We're approaching something that looks decent. And then we ask ourselves, well, what is the distance between these two charges? We are told that they are a distance d apart. And here I'm measuring to the center, but technically we could measure to the edges. Here it's not a big deal for physics 2. We could just say, okay, yeah, they're separated by a distance of d. And we can measure to their surfaces or towards their centers. They are slightly different numbers, but here they're just telling you they're separated by a distance d. And we just square that monster. And that is t sine of theta. Okay, so now we have this monster equation, and if we notice, well, shoot, they do not want the tension and showing up in our equations. We should cancel that out. Now here, if we get real clever, we notice, wait, tangent. Tangent is comprised of sine and cosine. As a matter of fact, it's sine over cosine. So let's take this quantity for t sine theta and divide it by the quantity for t cosine theta. And so combining these two and dividing them, we're going to get our answer for this part. And so we get k n squared q squared all over d squared. And I just kind of rewrote it here in not so pretty print, over mg, m times g. That is going to be t sine of theta over t cosine of theta. These cancel. Let's do that in Poiple. Just realized we got a little purple and green theme here going on. And so this becomes, well, we have a divisor here and we're dividing mg, and then we finally get their answer, n squared q squared all over. Oh, I forgot the 4. Just slap it in there. 4 d squared mg equals tangent theta. Let me know if I lost you anywhere. You guys are all ballers from Physics 1, so I think the algebra and the substitution here is manageable. We did a couple of these tension problems in Physics 1, and I think we had one of these in Quest, so hopefully it's not too much of a stretch for y'all. Because if it is, cancel your EP exam. I'm just kidding. Okay. Let's go ahead and take a look at the next part. It looks like we don't have any questions. The students want to create a linear graph from the experimental data to determine whether the same amount of charge is deposited on sphere 1 each time that it is rubbed with the cloth. Based on the explanation in part B, section 2, what quantity should be plotted on the horizontal axis and what quantity should be plotted on the vertical axis to produce a useful graph? So let's just go ahead and rewrite the expression. So even if we didn't do that algebra, we should be thinking, okay, they gave us this equation, and this equation shows the relationship of the experiment. So just to rewrite it, we get tangent of theta equals k n squared q squared all over 4 and not 4 d squared mg. Let me just make sure I wrote that down correctly. mg d squared. Okay, same thing. All righty. So let's go ahead and see here. What are they going to be changing in each trial? Well, they told us that in each trial, and so that's kind of how we identify our horizontal variable, because there's a couple of things that could be changing here. The important thing here is they want to find out whether the same amount of charge is deposited each time it's rubbed. So we want to see if Q is the same amount for every N, for every time it is rubbed. So they're going to increase N, the number of rubs. And then they're going to measure the deflection, so here we should be thinking which increases charge the overall charge on these spheres and the repulsive force between them. And this repulsive force is going to be demonstrated by tangent of theta. So it looks to me like, well, we're going to try to linearize this data. So I think in our experiment, we can kind of rewrite this as tangent of theta is going to be given by K Q squared all over 4, and I'll write it like they are, mg d squared times n squared. So that hopefully it's a little easier to see. Well, this is y. All of this is m. And then this is x. So what are we going to plot on the horizontal axis? Well, it's the thing we're changing, and we're changing the number of rubs. But to get a linear relationship out of this, and they're not asking exactly. Oh, yeah, they are. They say a linear graph. Want to create a linear graph. But to get a linear relationship, we see that tangent of theta is proportional to n squared, not theta is proportional to n. Really important. If we were to plot theta versus n, that is not linear. And that's because theta is not proportional to n, but to n squared. Let me know if we have any questions so far. Okay, I think I may need to minimize my OneNote because it's crashing. Oh, geez. So we're going to say on the horizontal axis, we should plot n squared, and then on the vertical axis, tangent of theta. Any questions so far? Ooh, I didn't paste their solution for the next. Yeah, it's the same thing I did. And yeah, they say the same thing here, whatever. The other one is just like really big to paste. And it's like the exact same work I did. And here's like, well, the exact same thing I said. Alrighty, next. How could the graph be used to determine whether the same amount of charge, is deposited on sphere 1 each time it is rubbed? So just because we're saying that this is going to be a linear graph, if Q does not increase by the number of times it's charged, like let's say I rub it once, I deposit 1 Q of charge. If I rub it twice and I get maybe 3 Q of charge, and then if I rub it 4 times, somehow I get like 20 Q of charge or some weird number, then that won't be a straight line graph. And that would tell us that Q is changing with each rub. So we could say if the graph of tangent of theta versus n squared yields, that sounds very fancy, yields a linear relationship. I didn't want to say graph because I already used the word graph earlier. Relationship. Then the amount of charge deposited each rub after each rub is the same. And then they ask, well, let's see here. How could the graph, so we look at then, so we could even say the slope of this graph would be k q squared all over 4mgd squared. So we could say q is going to be given by square root of the slope, and I don't want to write m because that's going to get confusing, times 4 times m times g times d squared all over k. And I don't think they ask for this. They just want us to see, well, how could the graph be used to determine? So we could say if it yields a straight line graph, the slope that tells us that the same amount of charge is deposited each rub. And if we wanted to find out exactly how much that quantity is, then we would get the slope and do that math to it. Any questions? If I'm moving too fast or too slow, let me know. I'm looking at the time and we're actually moving a little faster than anticipated. This is supposed to be like a 25-minute question, and even by explaining and doing all this, it's taking us about maybe 30 minutes. So I do feel like we're going a little faster. Usually these take me about 45 minutes to explain. Okay. We're good then on this one? I mean, I'm good. Alrighty, okay. So then we'll go ahead and jump to the next question here. So this is a short free response. This one's about 15 minutes. And so we have, from the looks of it, 2 plates and a couple of points here, A and B. Oh, this one's 20 minutes, sorry. 2 parallel, oppositely charged plates are shown in the side view figure. Points A and B are 2 locations between the plates. On each dot, draw a vector representing the electric field at the labeled points. The lengths of the vector should indicate the approximate relative magnitude of the electric field at 2 points. So do you guys want to take a stab at this one? Okay, alrighty. I think we'll go ahead and get started with this one. So one of the important things to understand is that if you have a plate, generally the electric field for a plate is going to be considered to be constant with distance, and that's really weird. But especially if we happen to have another plate here, we can go ahead and say that, okay, if this field were to drop off as it points away, this field will pick it up because it points inwards. So if we remember, when we're drawing electric fields, the idea is the electric field points away from positive towards negative. The idea being, what would a positive charge do? Well, a positive charge would move away, and so it would feel a force away from positive towards negative. So on here, both at points A and B, we're going to have an arrow that points up. Now, because the electric field is constant, these guys need to be the same length. So that's a big part. For a plate, the electric field, and we derived this expression when we were in in class, but it's something like sigma, the charge density, all over 2 epsilon naught, which is essentially, this here is the charge density. We may not remember that, but it can be thought of as, well, the charge density, we have some charge distributed over the area of a plate. So this is going to be, oh, sorry. And then like, there's a pi in here, actually. And we'll leave it like this. So it's going to be like Q over A all over 2 epsilon naught. Like this. You know what? Let me just Google it real quick because I feel a little unsure. Field for an electron. Okay, no, yeah, we're good. Okay, let's go ahead and continue. So because there's no distance factor in this, that's not going to change anything here as we move away from point A to point B towards the other plate. So we're fine here. Okay, let's go ahead and look at the next one, or the next question. A proton of mass MP is released from rest just above the lower plate and reaches the top plate with a speed Vp. An electron of mass Me is released just below the upper plate, and they want us to calculate the speed Ve of the electron when it reaches the bottom plate in terms of the velocity of the proton, the mass of the proton, and the mass of the electron, and physical constants as appropriate. And we can go ahead and ignore gravitational effects. It's released just above the lower plate, and so we're going to release our proton just to visualize this. We're going to release a proton just above the lower plate, and it's going to accelerate away from here, and it's going to have some velocity right before. And then they also tell us that we're going to release an electron just below the top plate, and it's going to accelerate away from the negative towards positive here. And so here we should be thinking, well, how the heck are we going to do this? They're talking about velocity and mass. So we can go ahead and think about, velocity and mass. So if we look at this, we should know that there is an electric potential difference between the plates. And so, for instance, the electric potential here would be maybe like 0, 5, 10, 15 volts. And I just made these numbers up. But there's an electric potential difference of 15 volts from one plate to the other. And it really doesn't matter which way, well, these numbers should increase as we move towards positive by the definition of electric potential difference. But the important thing here is they are both going to exchange the same amount of electric potential. Now, if we remember, electric potential, let me change the color here. Electric potential, we said, is calculated by KQ over R. The problem is this is for a point charge, because the electric potential is going to change with the distance that that you move away from it. So for a plate, the better way to think about it is we take this, one way we can get the electric potential is to take the electric field, which is KQ over R squared, and we do the integral of this bad boy along some distance, dr, which is not very handy for this class because we do algebra. But another way we can think about it is the work. So the voltage is the work done along or against an electric field while this charge moves at a constant velocity. Sorry, I'm getting ahead of myself. And the work we have seen, sorry, this is the electric potential energy. I'm kind of going all over the place. I am sorry, guys. The electric potential energy is going to be the work done against an electric field. And so the electric potential energy is going to be the force times the displacement. Now, electric potential is the electric potential energy per charge. And so if we look at this, this is going to be the force per charge times the displacement. And if we remember the definition of electric field, the electric field is the electrical force per charge. Because if we look at this electric force, Coulomb's law, is K Q1 Q2 all over R squared. So in this instance, we have an expression for the electric potential in terms of the electric field. And the reason we can do this is because the electric field is constant. And we usually write it as the electric field is the electric potential difference is the electric field times the displacement. So if we look at these, we can go ahead and say, well, we can combine a couple of ideas. For instance, electric potential is electric potential energy per charge. And in this case, all of the electric potential energy is going to become kinetic energy. So we can go ahead and say U is V, and really these are like delta V's, but I feel like a lot of times they don't write that in the books and people can get very confused by it. It's kind of like when people say acceleration is velocity over time, it's like, well, it's technically the change, but whatever. So we're going to go ahead and say that the electric potential here times the charge is going to become the kinetic energy, 1/2 mv squared. So let me know if we have any questions, because we're going to do some substitutions here for the proton. What this becomes is the voltage, or the electric potential difference, times the charge of a proton, which do they, okay, well, it's just going to be Q. Equals 1/2 m of the proton times the velocity of the proton squared. For the electron, and here we're just looking at magnitudes because this is the energy here, okay? So the electric potential, this guy for the proton is going to be, if we look at how the proton moves, it's going to go from 15 to 0. So the electric potential difference for the proton is going to be 0 volts minus 15 volts, or negative 15 volts. The electric potential that the electron experiences, well, it's going to go from 0 to 15. So it's going to be 15 volts minus 0 volts equals 15 volts. And so you may be thinking, well, how can we set them equal to each other at the end if they're going to, one's positive, one's negative? Well, here, this guy is negative 15. Let me make sure. Yeah. This guy is negative 15 volts, and this guy is positive. And then this guy is going to be 15 volts times a negative charge. So they both have the same magnitudes, and technically they're both going to be negative quantities, but it won't really matter. So this is going to be the electric potential times the charge of the electron equals 1/2 m velocity of the electron squared. And then we can go ahead and set these guys equal to each other. 1/2, because they have the same potential difference and the same charge magnitude, we can set these equal to each other, and they're negative quantities. Negative 15 times the elementary charge is going to be equal to 15 times the negative elementary charge. And so we can just set these two quantities equal to each other. 1/2 the mass of the proton times the velocity of the proton squared. And let me just scroll over real quick. Equals 1/2 the mass of the electron times the velocity of the electron. And the 1/2s don't cancel. And I believe they want us to solve for the velocity of the electron. Yeah. And we get the velocity of the electron is going to be equal to the mass of the proton over the mass of the electron times the velocity of the proton squared, square rooted. And so now we have our answer. You could kind of clean this up a little bit and say the velocity of the electron is going to be the square root of the masses divided times the velocity of the proton, because this guy's positive, squared already. And so there's our answer. Any questions, y'all? I think I'm going to move this over just to be able to fit it all in one fair glance. What the heck? Okay, looks like we're good. Let's go to question C now. The plates are moved further apart with each plate maintaining the same net charge. In a coherent paragraph length response, apply concepts of work and energy to explain how the electric potential difference between the plates changes, if at all, when the plates are moved further apart. Well, let you guys think about this for a second. How would the electric potential difference change if we pull them apart? I'm going to paste the explanation for the other part right here, real quick. Oops. What the heck? Yeah. So it's the same thing, electron. Okay, so let's see here. Well, if I have a positive and a negative plate in the vicinity of each other, in a normal circuit like a capacitor, these two plates don't snap towards each other, even though they are attracted to each other because they're held in place by like soldering and stuff like that. But very important, these two plates are attracted to each other because one is positive and one is negative. So for us to pull them apart, we need to do work on them. We're going to exert a force, and as we stretch them apart, there's a displacement to this force. So we are doing work on these plates, which means that when we do work, we are changing the energy in them. Now, if we look at this scenario, we have seen that the electric potential for parallel plates, the electric potential difference is given by the electric field times the distance between them. Now, this only works if the electric field is constant, which is the case here. It's not going to change. Even though we pull these plates apart, the field is determined by the charge on those plates. And the amount of charge we can deposit on a plate is just a factor of its geometry, how big it is. So if we don't change the size of the plates, we don't change how much charge we're putting on it. So we're going to keep the electric field the same. So we could say if the plates don't change size, the amount of charge they hold, we'll say, remains constant. And the electric field will also remain constant. Really important. The electric field had a constant value between the two plates. And as we move them further apart, one, it stays constant with distance, but it also remains constant with charge. Also remain constant. Now we got to talk about work and energy. So as a force pulls the plates, let's go ahead and look at the direction of the force. We're pulling with a force in this direction, and we're going to have a displacement in that direction. We are doing positive work on both plates. As the force pulls the plates, it does positive work on the plates. Increasing. Now, they're not going to gain kinetic energy. We're just changing the electric potential energy here because we're changing the electric potential. Increasing the electric potential energy of the plates. If we remember, work is equal to the change in energy, and that could be the change in kinetic plus the change in potential energy. In this case, we're not going to worry about the change in kinetic energy. We're going to change the electric potential energy here. Now, another way to think about it is as D increases for a constant electric field, the electric potential in the plates, or across the plates, I think is better, because electric potential is voltage, and we usually use the word across when talking about voltage. The electric potential across the plates increases. So a charge would have more electric potential energy. So there's like two ways to think about it. But because they asked us to apply the concepts of work and energy, we really want to think about this other paragraph here. But it works out because the electric field here is constant. Go ahead and post what they were thinking at the College Board. Oh, and then here, because U equals Q times delta V. And that's like delta Q. Okay. So the plates have opposite charges and are attracted to each other. So an external force must act on the system to increase the distance between the plates. The work done by the external forces increases the internal energy of the two-plate system. Each charge on a plate moves through a potential difference because its distance from the charges on the other plate changes. The change in internal energy is proportional to the charge of the system and the change of the potential of the system. The charge on the plate does not change, so the potential difference increases. So, ta-da. Alrighty, so we did it with about 6 minutes to spare. Hopefully this made sense. If you have any questions, let me know. Other than that, we're done for today.